In the autumnal landscape of 1943, a Republic P-47 Thunderbolt found itself unceremoniously grounded in a French field, a silent testament to a recent aerial skirmish. Its formidable propeller was bent into a contorted shape, and its landing gear had buckled beneath it, yet the aircraft's overall structure remained remarkably intact, a surprising resilience for a machine that had just endured a low-level strafing run. The pilot, having successfully bailed out, had inadvertently bequeathed this colossal, 7-ton marvel of American engineering to the waiting arms of the Luftwaffe, transforming it from a tool of Allied air superiority into a prize for enemy intelligence. Within mere hours of its discovery, a German recovery team descended upon the crash site with the fervor and precision of archaeologists unearthing an extraordinary, perhaps even extraterrestrial, artifact. While they were no strangers to the sight of downed Allied aircraft, having previously encountered the nimble Spitfires, the distinctive P-38 Lightnings, and even the formidable B-17 Flying Fortresses, the Thunderbolt presented a uniquely compelling enigma. Its sheer scale was astonishing, almost grotesquely ponderous for a single-engine fighter, and its reputation had, through a mixture of rumor and first-hand accounts from Luftwaffe pilots, swelled to almost mythical proportions, suggesting an adversary of unparalleled toughness. The actual recovery operation was executed with meticulous care, a delicate dance of engineering and logistics. German mechanics, displaying a profound respect for the captured technology, carefully disassembled the major components that could be separated without further damage. These substantial sections were then methodically loaded onto flatbed trucks and painstakingly transported to Rechlin, the Luftwaffe's principal testing facility, situated approximately 60 miles north of the bustling metropolis of Berlin. Rechlin was far more than a mere airfield. It served as the very nucleus of German aviation intelligence, a place where captured enemy aircraft underwent an exhaustive and rigorous analysis. By the twilight of 1943, this facility had evolved into a truly bizarre museum, a surreal tableau of Allied air power, where American, British, and Soviet aircraft stood in stark juxtaposition with German prototypes, each representing competing philosophies in the brutal air war. Stay with us and watch the end of the video. We will be grateful for your like and subscription. The arrival of the P-47 at Rechlin ignited an immediate surge of excitement among the facility's technical staff and its cadre of seasoned test pilots. For many months, disturbing reports had been filtering back from the Western Front, painting a consistent and troubling picture. Luftwaffe pilots repeatedly asserted that American fighters, particularly these imposing Thunderbolts, possessed an uncanny ability to absorb a level of punishment that would unequivocally obliterate a Messerschmitt Bf 109 or a Focke-Wulf Fw 190. Pilots recounted emptying entire ammunition loads into these P-47s during the heat of combat, witnessing their cannon shells impact with undeniable force, only to observe the American fighter continue its trajectory as if utterly impervious to damage. Some pilots, grappling with these perplexing observations, began to suspect their ammunition was defective, while others pondered whether American metallurgy had somehow achieved a revolutionary leap beyond German capabilities. Among the more superstitious, hushed whispers circulated about the Americans having developed some clandestine form of force field technology. German intelligence officers, facing mounting pressure, urgently required definitive answers. The relentless and resource-intensive conflict on the Eastern Front was consuming military assets at an astronomical pace, and the Luftwaffe simply could not afford to squander precious ammunition on aircraft that appeared to defy conventional destruction. If the P-47 genuinely harbored some revolutionary defensive technology, Germany's strategic imperative was clear. They needed to comprehend its workings, replicate it if possible, or devise effective countermeasures. The captured Thunderbolt thus presented an invaluable opportunity to unravel this profound mystery through direct, empirical examination, moving beyond mere battlefield conjecture and into the realm of scientific inquiry. What rendered this particular aircraft exceptionally valuable was its remarkably preserved condition. Unlike the majority of captured planes, which typically arrived as twisted, irreparable wreckage necessitating extensive and time-consuming reconstruction, this P-47 required only relatively minor repairs to be rendered airworthy once more. The massive engine remained miraculously intact. The robust airframe exhibited no significant structural damage, and most of its intricate internal systems appeared to be fully functional. German mechanics, scrutinizing the fighter, optimistically estimated they could have it soaring through the skies within a matter of weeks. More crucially, its excellent state allowed them to subject it to the kind of rigorous, even destructive, testing that promised to reveal precisely why these aircraft consistently survived combat damage that, by all logical standards, should have proven fatal. The stage was thus meticulously set for what would become one of the most profoundly revealing aircraft evaluations of the entire Second World War. The P-47 Thunderbolt was never conceived with aesthetic beauty as its primary objective, nor was it ever intended to be a lightweight design marvel. When Republic Aviation's dedicated design team convened in 1940, tasked with engineering a formidable fighter around the colossal Pratt & Whitney R2800 double wasp engine, they made a pivotal and conscious decision that would indelibly shape every subsequent aspect of the aircraft's development. Paramount survivability would unequivocally take precedence over any notion of aerodynamic elegance or nimble agility. The R2800 itself was an absolute behemoth, an 18-cylinder radial engine capable of churning out a staggering 2,000 horsepower, a figure that would later be incrementally boosted to over 2,500 horsepower in certain advanced variants. To contextualize this immense power, one need only compare it to its German contemporaries. The Bf 109G, for instance, produced approximately 1,475 horsepower, and even the potent FW-190A topped out around 1,700 horsepower. The Thunderbolt possessed a raw, unadulterated power output that German fighter aircraft simply could not match. However, such prodigious power inevitably came with its own set of significant consequences. The P-47D, which would become the most ubiquitous and widely deployed variant, tipped the scales at an approximate 10,000 pounds when empty, and could swell to a staggering 17,500 pounds when fully laden with fuel, ammunition, and its formidable ordnance. This made it, in essence, roughly twice as heavy as a standard Bf-109. German engineers, meticulously examining the captured aircraft, initially found it almost inconceivable that a single-engine fighter could carry such an immense weight and still operate with any degree of effective performance. Their own design philosophy, by stark contrast, rigorously emphasized lightweight construction and inherent agility, prioritizing the ability to outturn an opponent in the close quarters, knife fight style of dogfighting. The Americans, it appeared, had adopted an entirely antithetical approach, constructing what was, in all practical terms, a veritable flying tank. The colossal dimensions of the Thunderbolt stemmed, in part, from its sophisticated turbocharger system. Unlike German fighters, which typically employed mechanically driven superchargers mounted directly onto the engine block, the P-47 utilized a massive General Electric turbocharger strategically positioned in the aircraft's rear fuselage. Superheated exhaust gases, expelled from the engine, spun a powerful turbine which, in turn, drove a compressor, effectively forcing a dense stream of air into the engine at high altitudes, where the thin atmosphere would otherwise starve it of crucial oxygen. This intricate system necessitated extensive ducting, a complex network of pipes that traversed the entire length of the fuselage, conveying scorching exhaust gases rearward and compressed air forward. While the engineering was undeniably complex, heavy, and somewhat prone to leaks, it endowed the Thunderbolt with truly phenomenal high-altitude performance capabilities. At an altitude of 30,000 feet, where the Bf-109s and Fw-190s struggled for breath and experienced significant power loss, the P-47 continued to produce its maximum horsepower with unwavering efficiency. The fuselage itself was constructed with the resilience of a veritable fortress. Republic's astute engineers, having meticulously studied combat damage reports from early war fighters, had conclusively determined that the vast majority of fatal hits occurred in remarkably predictable locations, specifically the engine, the cockpit, and the aircraft's vital fuel system. Consequently, they armored everything in these critical areas. The pilot was ensconced behind a quarter-inch thick steel plate integrated into his seat back, and further protected by bulletproof glass positioned directly in front of him. Additional armor plating safeguarded the engine against frontal assaults. The fuel tanks incorporated a truly revolutionary self-sealing design, featuring multiple layers of rubber that would ingeniously swell and effectively close bullet holes upon exposure to fuel. While this fundamental technology existed in British aircraft, the Americans had refined it to an exceptionally advanced degree, pushing the boundaries of passive defense. Beyond the robust armor, a remarkable degree of redundancy was meticulously engineered into every critical system. The P-47 boasted multiple fuel pumps, ensuring continued operation even if one failed. Backup electrical systems provided an extra layer of reliability, and control cables were ingeniously routed through disparate sections of the airframe, thereby preventing a single cannon hit from severing them all simultaneously. The elaborate cooling system for that colossal engine was strategically distributed across a large area, meaning that even localized damage would not precipitate immediate and catastrophic overheating. German fighters, by contrast, designed for minimum weight and maximum performance, possessed no such inherent redundancy. A single, well-placed 20mm shell could easily incapacitate a Bf-109's cooling system, compelling the pilot to shut down the engine within minutes or face the dire consequences of catastrophic mechanical failure. The German technicians at Rechlin understood the fundamental specifications of the P-47 even before they commenced their hands-on evaluation. However, comprehending numbers on a blueprint and experiencing the aircraft firsthand were two fundamentally distinct realities. Rechlin was not merely assigning random pilots to assess captured aircraft. The Luftwaffe maintained a highly specialized unit known as Circus Rosarius, named after its charismatic commander, Theodore Rosarius, specifically entrusted with the critical task of evaluating enemy equipment. By 1943, this unit had evolved into one of the most elite and respected groups within the entire Luftwaffe, staffed by battle-hardened combat veterans, who possessed not only the exceptional skill to fly, but also the profound ability to analytically dissect an aircraft's strengths and weaknesses from a crucial operational perspective. These individuals were not test pilots in the conventional peacetime sense. They were seasoned warriors who had survived hundreds of harrowing combat missions and could instantaneously discern whether a particular design feature would genuinely impact performance in the crucible of actual battle. Among the distinguished aces selected for the critical P-47 evaluation was Hermann Graf. By late 1943, Graf had amassed an astonishing record of over 200 confirmed kills on the relentless Eastern Front, cementing his reputation as one of Germany's most successful and revered fighter pilots. He had flown virtually every type of fighter, from the early Bf-109E models to the very latest Fw-190A8S, endowing him with an encyclopedic understanding of fighter aircraft handling characteristics across a broad spectrum. The Luftwaffe specifically sought pilots of Graf's caliber because they would not be swayed by mere novelty or intimidated by foreign technology. They would evaluate the Thunderbolt with the same cold, methodical detachment they applied to assessing a potential opponent in combat, meticulously scrutinizing it for any vulnerabilities that could be exploited. Alongside Graf, several other highly experienced and decorated pilots rotated through Rechlin for the rigorous evaluation. Hans Vera Leah, another distinguished pilot, dedicated considerable time to analyzing captured Allied aircraft and would later extensively document his invaluable experiences and insights. These elite pilots acutely understood that their meticulously crafted reports possessed the potential to significantly influence Luftwaffe tactics across the entire Western Front. Should they uncover a critical weakness in the P-47, perhaps an inability to execute tight turns at low speeds, or possibly discernible blind spots within the cockpit, that vital intelligence would be rapidly disseminated to frontline fighter squadrons within a matter of days. Conversely, if their comprehensive testing confirmed that the Thunderbolt was indeed as incredibly tough and resilient as frontline pilots claimed, the Luftwaffe would be compelled to fundamentally adjust its entire approach to engaging American fighter escorts. The comprehensive evaluation process at Rechlin adhered to a stringent, structured protocol. Initially, pilots would conduct thorough walk-around inspections, meticulously examining the aircraft's construction, its formidable armament, and its intricate systems. They would then meticulously study the cockpit layout, carefully noting where American designers had strategically placed critical controls, and how the cockpit visibility compared to their own German fighters. Following this, ground engine runs were performed to ascertain the power plant's unique characteristics. Only after this exhaustive preliminary assessment would they attempt actual flight testing. Even the flight tests followed a careful, progressive sequence, beginning with short hops around the airfield, gradually expanding to include complex aerobatic maneuvers, exhilarating high-speed dives, and meticulously simulated combat scenarios. The entire, painstaking operation was obsessively documented, leaving no detail unrecorded. I am from the United States, and I find the video topic fascinating. The detailed look at how the Luftwaffe analyzed captured Allied aircraft, particularly the P-47, provides an incredible insight into the technological and tactical chess match that was World War II. It's a reminder that intelligence gathering and reverse engineering were as crucial as direct combat in the struggle for air superiority. The captured American P-47 Thunderbolt, an aircraft of formidable reputation, was meticulously chronicled with an almost zealous dedication by German technical experts. These specialists captured exhaustive photographic evidence of every component, meticulously recorded precise measurements, and synthesized comprehensive technical dossiers destined for distribution among aircraft manufacturers and the highest echelons of Luftwaffe command. Their objective extended beyond merely dissecting a single enemy fighter. They sought to unravel the overarching principles guiding American aeronautical engineering as a whole. Crucial questions underpinned this intense scrutiny. What innovative attributes might German engineers glean from this sophisticated machine? Were there specific design features meriting adaptation or direct replication? Conversely, did it possess inherent vulnerabilities amenable to tactical exploitation in future aerial engagements? Beyond the purely technical evaluation, a significant component of psychological operations was woven into these assessments. The Luftwaffe, on occasion, deployed captured Allied aircraft in combat, emblazoning them with German markings and pitting them against Allied formations in an effort to sow disarray and uncertainty. A P-47 bearing Luftwaffe insignia, appearing unexpectedly in a contested sector, possessed the potential to induce momentary hesitation among American pilots, and any moment of indecision in the crucible of aerial combat frequently proved lethal. However, this deceptive tactic could only succeed if German pilots possessed an intimate mastery of the captured aircraft's flight characteristics, enabling them to credibly impersonate their American counterparts, at least from a distance. Thus, as the skilled Rechlin team prepared for their inaugural flights in the formidable Thunderbolt, they carried with them a formidable reservoir of combat acumen, forged over countless dogfights, coupled with an intense, almost palpable eagerness to ascertain whether this massive transatlantic interceptor could truly validate the increasingly formidable hearsay surrounding its capabilities. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Please write a comment about where you are from and what you think about the video topic. Hermann Graf maneuvered his frame with some effort into the P-47's cockpit and was instantly struck by the realization of why American pilots were generally required to be of reasonable stature. The cockpit, while not evoking feelings of oppressive confinement, actually offered a considerably more capacious interior volume than that of a Bf-109. Nevertheless, every control and display appeared ergonomically configured for individuals possessing greater limb length than the average German aviator. The rudder pedals were situated far forward. The control column rose from the floor at an unconventional inclination, and the instrument panel seemed to recede perceptibly into the forward expanse. German fighters, by contrast, typically enveloped their pilots with the snug precision of bespoke garments. The Thunderbolt, in this initial impression, conveyed an impression akin to occupying a modest chamber. The panoramic visibility afforded by the P-47's canopy was nothing short of revolutionary. This iconic bubble-shaped enclosure, a design innovation introduced with the D model, provided a nearly unimpeded 360-degree vista that rendered the heavily framed canopy of the Bf-109 akin to gazing out through a narrow aperture. Graf found he could effortlessly glance directly behind himself without straining, scan above and below with scarcely perceptible cranial adjustments, and enjoyed an unhindered perspective of both wingtips. In the demanding environment of aerial combat, such clarity of vision would represent an unparalleled tactical superiority. Luftwaffe pilots had discovered through arduous and often costly experience that the vast majority of aerial victories stemmed from attacks the victim never saw coming. The P-47's expansive canopy, therefore, rendered surprise attacks considerably more arduous to execute successfully. Initially, the instrument layout presented a perplexing challenge to the German aviators. American designers had adopted a fundamentally distinct organizational schema for their flight controls and indicators. Airspeed was measured in miles per hour rather than kilometers per hour, altitude in feet rather than meters, and a labyrinthine assortment of dials and indicators monitored systems that German fighters were entirely devoid of. For instance, a plurality of fuel reservoir selection mechanisms was present, reflecting the P-47's capacity to carry fuel in its fuselage, wings, and even external drop tanks. An intricate supercharger management apparatus, complete with a sophisticated network of regulating devices and pressure monitoring instruments, further complicated matters. The electrical panel alone boasted a greater profusion of toggle controls than the aggregate complement within the entire flight deck of a Bf-109E. It consequently required a considerable expenditure of hours for Graf and his fellow pilots merely to decipher the function of each control, and an even more protracted period to internalize the intricate engine startup sequence. The armament switch panel, in particular, clearly articulated another facet of American design philosophy, a doctrine prioritizing sheer, devastating offensive capability. The P-47D was equipped with 8 Browning M2.50 caliber machine guns, for symmetrically mounted in each wing, each supplied with an estimated 425 projectiles. This culminated in an approximate aggregate of 3,400 munitions. By comparison, a typical FW-190A8 usually carried 4 20mm cannons and 2 13mm machine guns, but with a significantly reduced overall ammunition capacity. The American approach, therefore, emphasized the sheer density of projectiles, aiming to create a veritable hail of leads so concentrated that rendering evasive maneuvers almost utterly futile. The German approach, conversely, emphasized penetrative force and destructive potential, fewer shots, but each one capable of inflicting devastating structural compromise. Neither philosophy was intrinsically ascendant. They simply underscored divergent operational methodologies rooted in distinct tactical doctrines. What most profoundly astonished Graf, however, was the unexpected level of comfort. The pilot's seat was generously cushioned, the cockpit was efficiently temperature-controlled, and there was even a discreet waste disposal system for protracted missions, a seemingly minor amenity that assumed considerable importance on 4-hour escort missions to Berlin and back. German fighters, by design, were optimized for brief, rapid-response interception sorties, seldom remaining aloft for periods exceeding 90 minutes. The P-47, conversely, was unmistakably engineered for protracted operational deployments, its ergonomics placing a premium on aviator stamina rather than absolute minimal mass. Adding to the pilot's ease, the control column featured integrated electronic trim controls embedded within the handgrip, empowering the pilot to fine-tune the aircraft's aerodynamic equilibrium without disengaging a hand to reach for separate trim wheels. This might appear inconsequential, yet, in the intense environment of combat, maintaining one hand on the throttle and the other firmly on the stick at all times could represent the decisive margin between survival and demise. The oxygen system presented yet another groundbreaking innovation. It utilized a sophisticated demand-based regulator that autonomously modulated oxygen flow based on altitude, starkly contrasting with German systems that necessitated continuous manual intervention. Again, a seemingly small detail, but one that significantly alleviated the operational burden on the pilot during the turbulent maelstrom of stratospheric engagements. It became abundantly clear that American designers had evidently meticulously considered every facet of the pilot's experience, engineering the aircraft for maximal operational simplicity, so that the aviator could devote their primary attention to tactical engagement rather than system administration. Graf hadn't even initiated the engine startup sequence yet, and already the Thunderbolt was fundamentally altering his preconceived notions regarding interceptor aircraft architecture. The formidable R-2800 double Wasp engine erupted into a sonorous, guttural roar, a sound markedly contrasting with the piercing shriek characteristic of a Daimler-Benz inline engine. Graf permitted the engine to reach optimal operating temperature, meticulously following the procedural guidelines the ground crew had painstakingly rendered from confiscated American technical documents, observing the indicators for cylinder head temperature steadily ascend into their designated operational zones. The entire aircraft quivered with an almost palpable, barely restrained kinetic energy, and he had not yet even initiated the forward thrust of the throttle lever. When he finally disengaged the braking mechanism and commenced movement toward the runway, the P-47's immense mass became instantly manifest. It did not exhibit the nimble ground handling of a Bf-109. Instead, it proceeded with a ponderous, deliberate motion, necessitating robust pressure on the braking pedals to control speed and decisive, short applications of engine power to initiate movement from a standstill. The takeoff roll proved more protracted than Graf had anticipated, even with that massive engine. The Thunderbolt gained velocity with consistent progression, yet without a sudden, violent surge, its sheer weight demanding a greater expanse of paved surface than any single-engine fighter he had previously commanded. Approaching 100 miles per hour, he gently retracted the control column, and the P-47 ascended gracefully into the air, soaring skyward from the Rechlin airfield with a profound inherent stability, reminiscent of handling a larger bomber aircraft. There was none of the nervous responsiveness of a Bf-109, nor any inclination to yaw abruptly during initial acceleration characteristic of the powerfully torqued Fw-190. The Thunderbolt simply maintained its aerial trajectory with unwavering solidity and unwavering predictability. At altitude, the dynamic of flight underwent a profound transformation. Graf stabilized his flight path at an altitude of 25,000 feet and commenced assessing the aircraft's aerodynamic responsiveness. The controls demanded greater physical exertion than those of German interceptors. The ailerons, in particular, necessitated considerable muscular effort to maneuver at high speed, and the elevator felt akin to traversing a viscous, resistant medium compared to the delicate manipulation required in a Bf-109. Yet, there was an inherent accuracy embedded within that resistance. When Graf initiated a directional change, the P-47 executed the maneuver with the precise degree of deflection desired, then halted with devoid of any compensatory overshoot or oscillatory movement. It possessed such profound stability that it conveyed an almost disinclined attitude towards agile movements, but that very stability would prove exceptionally valuable as a stable ordnance delivery platform. German pilots frequently contended with difficulties in maintaining their sight picture during high-speed attacks because their fighters exhibited such acute responsiveness. The Thunderbolt's heavy controls, conversely, would ensure the unwavering stability of the aiming reticle upon the intended mark. Then Graf depressed the aircraft's nose and advanced the throttle to its full extent. This was the crucible from which the Thunderbolt's formidable renown had emerged, and the German pilots were compelled to ascertain the veracity of the prevailing narratives. The airspeed indicator ascended with swift alacrity. 300 miles per hour, 350, 400, 450. The aircraft maintained an unyielding, steadfast stability. There was an absence of any aerodynamic shuddering, or inclination to spontaneously pitch down or intensify its descent. At 500 miles per hour, velocities that would induce aerodynamic control surface oscillation and precipitate structural integrity anxieties in most German fighters, the P-47 continued to exhibit responsive handling. Graf retracted the control column to recover, and the Thunderbolt transformed its immense kinetic energy from the descent into a rapid, ascendant trajectory that propelled him skyward by several thousand feet within mere moments. This was the Thunderbolt's decisive combat superiority. In aerial combat, a diving attack followed by a zoom climb represented the most secure and efficacious aerial combat maneuver. The attacker plunged upon his quarry with prodigious velocity, discharged a concise volley of ordnance, then utilized that acquired speed to regain a higher operational ceiling before any counterattack could be mounted. The P-47 could achieve greater diving velocities than any aircraft in the Luftwaffe's inventory, and could maintain such velocities for more extended durations. A Bf-109 pilot attempting to follow a diving Thunderbolt would either have to abandon the chase or hazard compromising the structural integrity of his own machine. And even if a German pilot did manage to catch a P-47, the American could simply advance the throttle forward and disengage, utilizing its inherent speed advantage to sever contact. Conversely, the aircraft's maneuverability in turning engagements presented a distinctly altered narrative. Graf initiated a tight, aggressive banking maneuver at medium altitude and instantly perceived the inherent constraints. The P-47 did turn, but it executed broad turns, dissipating kinetic energy with swiftness during prolonged rotational maneuvers. A Bf-109 or Fw-190 could effortlessly outmaneuver the Thunderbolt in a turning contest and achieve a favorable position for weapon deployment if the confrontation degenerated into a protracted dogfight characterized by circular maneuvering. But Graf came to a pivotal understanding. American pilots operating these aircraft would, in all likelihood, never permit such a scenario to unfold. Why would they? Possessing preeminent velocity, exceptional high-altitude capabilities, and remarkable zoom climb proficiency, P-47 pilots could unilaterally establish the parameters of aerial combat. They could selectively determine the opportune moments for initiating or breaking off combat, thereby compelling their German adversaries to contend on conditions dictated by American strategy. The assessment sorties persisted for several consecutive days, with a succession of aviators meticulously evaluating diverse facets of the Thunderbolt's operational capabilities. A unanimous verdict swiftly emerged. This formidable machine was not conceived as a conventional dogfighter, akin to its European counterparts, yet it proved to be an exceptionally lethal combat aircraft when its inherent strengths were judiciously leveraged. These extensive flight trials successfully elucidated numerous queries pertaining to its performance metrics, but one profound enigma remained stubbornly unsolved: the astonishing resilience of these aircraft in the face of damage that, by all rational expectations, should have rendered them utterly irrecoverable. Luftwaffe pilots were unequivocally not succumbing to flights of fancy. Genuine combat footage, captured by gun cameras, unequivocally depicted 20mm cannon shells striking P-47 squarely, generating vivid, explosive impacts upon contact. Despite these devastating blows, the American fighters conspicuously maintained their aerial integrity. A significant number of these battle-scarred machines eventually limped back to their home bases, bearing scores of perforations, extensively lacerated control surfaces, and severely compromised engines, only to be meticulously repaired and miraculously take to the skies once more on the subsequent day. German intelligence agencies were therefore compelled to ascertain whether this extraordinary durability was merely a product of sheer fortune, indicative of superior construction methodologies, or perhaps attributable to some distinctive design characteristic that could be effectively counteracted. We sincerely invite you to remain with us and witness the dramatic conclusion of this compelling video. Your like and subscription would be immensely appreciated. Please also consider leaving a comment detailing your geographical origin and your thoughts on the intriguing subject matter of this video. The highly skilled team at Rechlin ultimately resolved to adopt a forthright methodology. Their plan involved directly engaging the impounded P-47 with their indigenous weaponry, and meticulously scrutinizing the precise repercussions. Such an undertaking was not entirely unprecedented. The Luftwaffe had, on prior occasions, conducted comprehensive weapons effectiveness assessments on confiscated aircraft, typically by securely affixing the target airframe onto a stationary stand and discharging ordnance at it from an array of different vantage points. However, the forthcoming P-47 evaluation was destined to be considerably more exhaustive in its scope. Their intention was to systematically target critical operational systems, including the engine, the fuel reservoirs, the intricate control surfaces, and the pilot's cockpit area, meticulously documenting the precise threshold of damage the aircraft could withstand before becoming unequivocally incapacitated and unflyable. The principal armament designated for this rigorous testing regimen was the MG-151/20, the ubiquitous 20 mm cannon that constituted the standard offensive weapon in the majority of Luftwaffe fighters by the year 1943. This formidable weapon propelled a 115-gram high-explosive incendiary projectile at an approximate muzzle velocity of 720 meters per second. In the crucible of aerial combat, a solitary, accurately placed strike from an MG-151/20 possessed the destructive potential to obliterate vital components, sever crucial control cables, or instantaneously ignite fuel tanks. Most German aviators generally concurred that between 3 and 5 solid hits were entirely sufficient to bring down any Allied fighter aircraft. The FW-190A8, for instance, was equipped with 4 such cannons, endowing it with truly devastating firepower, albeit tempered by a comparatively limited ammunition supply of approximately 250 rounds in total across all 4 weapons, providing roughly 5 seconds of continuous discharge. The meticulous arrangement for the test necessitated extremely careful foresight and logistical coordination. German engineering specialists precisely positioned the P-47 on the expansive Wustrow firing range, ensuring its absolute immobility to preclude any unintended movement, yet simultaneously guaranteeing that all its intricate systems remained readily accessible for thorough post-test examination. They judiciously filled the aircraft's fuel tanks with authentic aviation fuel, aiming to rigorously assess the efficacy of this self-sealing technology under the most realistic conditions conceivable. The cockpit interior was comprehensively instrumented with an array of pressure sensors and high-speed cameras, designed to meticulously record every eventuality when projectiles traversed the pilot's immediate vicinity. They even went so far as to install a meticulously constructed dummy in the pilot's seat, strategically positioned directly behind the protective armor plate, with the explicit objective of discerning whether the aircraft's defensive systems genuinely offered any practical protection. Multiple MG-151/20 cannons were strategically mounted at various positions around the perimeter of the aircraft, meticulously calibrated to simulate a diverse range of potential attack angles. In the dynamic reality of actual combat, fighter aircraft seldom engaged from perfectly perpendicular trajectories. The overwhelming majority of attacks typically originated from the rear quarter, either marginally above or below, as the aggressor diligently endeavored to close the distance into effective firing range while simultaneously evading the target's defensive fire. This comprehensive test was specifically engineered to precisely replicate these characteristic angles, with rounds being discharged at the engine from a shallow angle that faithfully mimicked a typical pursuit attack, impacts delivered to the wings from the flank to rigorously test the vulnerability of the fuel tanks, and strikes directed at the tail section to observe how the intricate control systems responded to sustained damage. The judicious selection of ammunition was equally paramount to the integrity of the experiment. German 20 mm rounds were manufactured in several distinct variants. Armor-piercing projectiles specifically designed for engaging heavily armored bombers, high-explosive incendiary rounds optimized for aerial combat against enemy fighters, and mixed belts that judiciously alternated between these different types. The test protocol stipulated the exclusive use of combat-loaded ammunition, precisely the same mixture that Luftwaffe pilots routinely carried on their actual operational missions. This included the notorious Menengescus rounds, which were characterized by their remarkably thin walls and an exceptionally generous payload of explosive material, far exceeding that of typical cannon ammunition. These particular rounds proved devastatingly effective against aircraft, possessing the inherent capability to inflict colossal damage with a single, well-placed hit. A diverse assembly of observers, representing various technical branches from across the Luftwaffe, converged upon the test site. This undertaking transcended mere academic curiosity. Should the P-47 demonstrate a particular susceptibility to specific attack methodologies, that invaluable intelligence would be immediately disseminated and exploited. Conversely, if it proved remarkably resistant, the Luftwaffe might be compelled to embark upon the development of entirely new ammunition types or innovative tactical doctrines. There was also a palpable undercurrent of concern regarding the allocation of scarce resources. Germany was already experiencing considerable strain in its efforts to manufacture a sufficient quantity of aircraft and ammunition to sustain its campaigns on multiple fronts. If the current arsenal of weapons proved ineffectual against the formidable American heavy fighters, the Reich simply could not afford to persist in squandering precious ammunition on attacks that failed to yield tangible results. With meticulous precision, the test crew loaded the cannons, rigorously verified the flawless operation of all measuring equipment, and braced themselves to definitively ascertain whether the P-47 Thunderbolt truly possessed the legendary indestructibility it appeared to embody. The initial cannon discharged with a sharp, resonant crack that reverberated across the expansive Rechlin test range, propelling a 20mm shell directly into the P-47's engine cowling. The impact was virtually instantaneous, manifesting as a brilliant flash of orange as the high-explosive round detonated, immediately followed by the appearance of a conspicuous hole punched clean through the metallic surface. The assembled observers diligently noted the initial results, and then made ready for the subsequent shot. This was unequivocally not intended to be a singular bullet test. Their comprehensive plan involved subjecting the Thunderbolt to the precise kind of sustained, concentrated fire it might realistically encounter during an actual combat engagement, systematically emptying multiple cannon magazines into various critical areas to accurately simulate a determined and relentless assault by a highly experienced pilot. An increasing number of rounds subsequently slammed into the engine section, originating from a multitude of different angles. Each individual impact invariably created a distinct and discernible pattern of damage. Some rounds cleanly perforated the structure, leaving clearly defined entry and exit holes, while others detonated internally within various components, generating extensive fragmentation damage that radiated outwards from the point of impact. The colossal R-2800 engine absorbed hit after relentless hit with astonishing resilience. Cylinders visibly cracked, cooling fins shattered into fragments, and substantial chunks of the cylinder head broke away. The accessory section, where vital generators and hydraulic pumps were securely mounted to the engine, sustained several direct impacts. By any conventional metric or expectation, this engine should have been utterly and completely destroyed, rendered irrevocably inoperable, a total and irrecoverable loss. The German gunners then meticulously shifted their aim towards the wings, specifically targeting the aircraft's fuel tanks. This was the juncture where, by all logical assumptions, the situation should have escalated into a catastrophic event. Aviation fuel is inherently volatile, and the 20mm high-explosive incendiary rounds were expressly engineered to ignite fuel tanks with devastating efficiency. A single, accurately placed hit on an unprotected tank would typically transform an aircraft into an instant fireball. The Luftwaffe had witnessed countless Allied aircraft erupting into spectacular mid-air explosions after a fortuitous cannon hit found its mark on a vulnerable fuel tank. The P-47, however, was equipped with multiple fuel tanks strategically located within both its wings and fuselage, boasting an impressive total capacity exceeding 300 gallons. One well-aimed hit, it was widely presumed, should have been more than sufficient to transform this formidable aircraft into a raging inferno. The very first 20mm round struck the left-wing tank with unerring precision directly in its center. The expectant observers anticipated an immediate, violent explosion or, at the very least, unmistakable visible flames. Instead, they merely witnessed fuel spraying conspicuously from both the entry and exit holes, creating a fleeting mist in the ambient air, and then, astonishingly, nothing further. There was no fire, no explosion. The fuel simply began to leak out, gradually, pooling on the ground directly beneath the wing. The gunners, perplexed, fired repeatedly, punching numerous additional holes through the wing tanks from a variety of different angles. Each successive impact resulted in more fuel leakage, yet still, there was no ignition whatsoever. The self-sealing technology was unequivocally performing its function, but, even more remarkably, the high-explosive rounds were evidently failing to generate the precise fuel-air mixture necessary to initiate combustion. The tanks, it became apparent, were ingeniously designed with sufficient internal structural integrity that even explosive cannon shells could not inflict the kind of catastrophic damage required to ignite the fuel. Attention then pivoted towards the cockpit area. German fighter aircraft typically possessed only minimal armor protection, and consequently, a 20mm hit anywhere in the immediate vicinity of the pilot's position was almost invariably fatal. The P-47's substantial armor plate, strategically positioned behind the pilot's seat, was primarily designed to effectively stop rifle-caliber rounds and high-velocity shell fragments. However, could it withstand a direct impact from a 20mm cannon? The unequivocal answer was no. A direct hit squarely on the armor plate would indeed penetrate it. Yet, the subsequent testing revealed something far more intriguing. The armor was positioned and angled in such a sophisticated manner that a direct, perfectly perpendicular hit was rendered exceedingly improbable. The vast majority of rounds struck at oblique angles, and even in instances where they did manage to penetrate, the armor possessed the remarkable property of deflecting them sufficiently, ensuring that the dummy occupying the pilot's seat remained comparatively well protected. The tail section was subjected to a brutal and exhaustive assault next. Critical control cables, vital hydraulic lines, and the fundamental structural components that securely affixed the tail surfaces to the fuselage all sustained direct impacts. The rudder was utterly shredded, reduced to fragments. The elevator bore multiple gaping holes punched clean through its surface. And the vertical stabilizer, in its damaged state, presented an appearance akin to having been savagely attacked with a colossal cheese grater. This was precisely the kind of extensive damage that would, under normal circumstances, render most aircraft completely unflyable. Control surfaces, by their very nature, require smooth, aerodynamic integrity to function correctly and efficiently. Any significant compromise to their structure should, theoretically, severely impair the pilot's ability to maintain control of the aircraft, particularly at elevated speeds where aerodynamic forces dramatically amplify every imperfection. After approximately 50 20mm rounds had been systematically discharged into various sections of the aircraft, the gunners finally ceased fire. Wisps of smoke drifted lazily across the test range, emanating from propellant residue and a few smoldering components, but there had been no catastrophic explosion, no massive, uncontrollable fire, nothing that remotely resembled a definitive combat kill. The P-47 remained defiantly in position, battered and riddled with holes, yet remarkably, structurally intact. The true measure of its resilience, however, would only become apparent during the meticulously conducted post-firing inspection, when engineers could thoroughly examine precisely what had endured and what had succumbed to the relentless assault. The inspection team, armed with their clipboards, cameras, and a profound sense of professional skepticism, approached the P-47, which bore the grim marks of numerous bullet impacts. From a distance, the aircraft presented a desolate image, appearing irrevocably damaged and seemingly beyond any hope of flight. However, as they drew closer, the extent of the destruction proved to be even more significant than their initial observations had suggested. The engine cowling, for instance, was so perforated that it resembled a colander, with jagged apertures revealing the intricate cylinder banks nestled within. The wings too displayed considerable harm, some of the holes gaping wide enough for a human fist to pass through. The fabric covering the tail section was reduced to tattered remnants, where it had not been completely obliterated by the force of the impacts. Yet, despite this widespread devastation, as the meticulous engineers commenced their systematic analysis, they were repeatedly confronted with a perplexing reality. While critical systems had sustained damage, they had remarkably not been utterly destroyed. The examination of the engine yielded the first substantial revelation. Indeed, numerous cylinders had been struck, cooling fins were fractured, and various accessory components lay shattered. However, the engine block itself, that colossal, exceedingly robust crankcase forming the very heart of the R-2800, remained astonishingly intact. German engineers quickly grasped that the sheer magnitude of this radial engine offered an inherent layer of protection. With its 18 cylinders arranged in a double row, the loss of even 2 or 3 cylinders still left a formidable 15 in operation. Consequently, while the engine might operate with a noticeable roughness and a significant reduction in power, it would nonetheless continue to function. This stood in stark contrast to a liquid-cooled inline engine, such as the DB605 found in a Bf-109, which lacked such a built-in redundancy. Damage to any single cylinder in such an engine typically resulted in a rapid loss of coolant, inevitably leading to overheating and a catastrophic seizure within mere minutes. Stay with us and watch the end of the video. We will be grateful for your like and subscription. What are your thoughts on this topic, and where are you from? Crucially, the P-47's oil system had also demonstrated an extraordinary resilience. While several oil lines had been severed and the oil tank itself showed clear signs of penetration, the system possessed sufficient capacity and an ingenious redundancy. This meant that even with substantial leakage, an adequate supply of oil would persist to ensure the engine remained lubricated for the vital minutes required to reach the relative safety of friendly territory. In contrast, German fighters typically carried smaller oil reservoirs, often situated in more vulnerable positions. A single 20 mm hit to the oil system of a Bf-109 was, in practical terms, a harbinger of the engine's demise. The inspection of the fuel tanks, however, arguably yielded the most astounding discovery. These were not merely self-sealing tanks with a rudimentary rubber coating. They were sophisticated, multi-layered systems. The outermost layer consisted of conventional aluminum, designed to maintain the tank's structural integrity and shape. Beneath this lay a layer of vulcanized rubber, followed by a layer of untreated rubber, which then encased the inner fuel. The ingenious mechanism operated such that when a bullet or shell fragment pierced the tank, the fuel would interact with the untreated rubber layers, causing them to rapidly swell and expand. This physical expansion effectively sealed the hole within a matter of seconds. German engineers had previously encountered self-sealing tanks in British aircraft, but the American implementation proved to be far more robust, capable of sealing larger breaches and enduring multiple penetrations. The rigorous test had inflicted approximately a dozen 20 mm holes across various fuel tanks, and every single one had either sealed completely or was in the advanced process of doing so. While fuel had undeniably leaked out initially, the flow had subsequently ceased or diminished to a negligible drip. More significantly, the tank's intricate structure had successfully prevented the kind of explosive fuel vaporization that commonly led to catastrophic fires. The internal baffles and foam filling present in some tanks meant that even high explosive rounds could not generate a sufficient fuel mist to ignite. An Allied pilot might indeed lose 20 or 30 gallons of fuel due to combat damage, but they would not, critically, lose their life to a devastating fire. The examination of the control system damage revealed an equally profound narrative. Multiple control cables had been completely severed, the very type of damage that should have rendered the aircraft utterly uncontrollable. Yet, the P-47 incorporated dual, and in some instances, triple, redundant control runs. The ailerons, for instance, were operated by two entirely separate cable systems routed through different sections of the wing. Similarly, the elevator and rudder were equipped with both primary and backup controls. This meant that even with several cables cut, at least one functional control path invariably remained. While the controls might become noticeably stiffer or less responsive, demanding greater physical exertion from the pilot, they would nonetheless remain operational. A damaged P-47 might present a formidable challenge to fly, but it would unequivocally remain flyable. Even the electrical system exhibited a remarkably thoughtful redundancy. The aircraft boasted multiple generators, several battery systems, and circuit breakers meticulously designed to isolate and protect damaged sections. In stark contrast, a Bf-109 suffering electrical damage would frequently experience a complete and simultaneous loss of all electrical power. The P-47, however, could lose half its electrical system and still maintain power to its most critical instruments and radios. The engineers meticulously documented every detail, capturing measurements, photographs, and samples of materials for subsequent, in-depth analysis. Their preliminary conclusion was both inescapable and profoundly humbling. The Americans had conceived and constructed an aircraft engineered from its very first rivet to withstand and survive the brutal realities of combat damage. This was neither a matter of sheer luck nor merely the use of superior materials. It represented a systematic design philosophy that unequivocally prioritized pilot survival and aircraft recovery above all else, even over minimizing weight or maximizing performance. The Germans, it became clear, had been designing fighters primarily to win individual dogfights. The Americans, on the other hand, had been building fighters with the explicit purpose of bringing their pilots safely home. The comprehensive technical report, meticulously compiled by the Rechlin engineers, spanned dozens of pages, yet its fundamental findings could be distilled into a single, damning sentence. The German fighter design philosophy had been fundamentally flawed for the particular nature of the war they were currently prosecuting. While the document, in typical military bureaucratic fashion, refrained from stating this quite so bluntly, the implications were undeniably clear to anyone capable of discerning the subtext. The P-47 embodied a radically different approach to aerial combat, one that consciously accepted certain compromises in exchange for overwhelming advantages in pilot survivability and operational endurance. The intricate analysis of the armor revealed a profound consideration for bullet trajectory and the probabilities of impact. American designers had not merely affixed steel plates haphazardly onto the airframe. They had meticulously studied the most probable angles from which enemy fire would originate during typical combat engagements and had positioned the armor accordingly. The seatback armor, for example, offered crucial protection against the most common attack angle from behind and slightly above. The windscreen armor shielded against head-on attacks and effectively deflected fragments resulting from engine hits. Even the thickness of the armor varied, carefully calibrated based on the likelihood of a threat. Critical areas received quarter-inch plating, while less vulnerable sections were afforded lighter protection. The Germans, too, incorporated armor, but it was minimal, often appearing more as an afterthought than as an integral and meticulously planned design element. The self-sealing fuel tank technology proved to be a source of immense fascination for German chemists and engineers. They painstakingly dissected sample sections and subjected the rubber compounds to rigorous analysis under laboratory conditions. The system's efficacy hinged on a specific chemical reaction between aviation fuel and untreated rubber. Upon contact with the fuel, the rubber layer would undergo rapid and significant swelling. This rubber could expand to several times its original volume, thereby creating a plug that effectively sealed holes up to approximately 12 mm in diameter. While larger holes might not achieve a complete seal, the system would still significantly restrict fuel flow. The Germans possessed similar technology, but their implementation was demonstrably inferior. Their self-sealing tanks frequently failed after enduring multiple hits, whereas the American tanks could sustain numerous penetrations and continue to function effectively. The philosophy of redundancy permeated every single system on the aircraft, and this concept was perhaps the most challenging for German engineers to fully comprehend. Redundancy inherently entailed additional weight, increased complexity, higher costs, and a greater maintenance burden. Within the German military-industrial complex, already stretched thin by the demands of a multi-front war, such apparent inefficiency seemed almost profligate. However, the American calculation was fundamentally different. The United States possessed an abundance of industrial capacity, plentiful raw materials, and a strategic philosophy that regarded highly trained pilots as irreplaceable assets. Building a heavier, more expensive fighter that reliably brought pilots home was considered a far superior investment than constructing lighter, cheaper fighters that ultimately led to higher pilot casualties. The report included detailed calculations concerning combat effectiveness. A Bf-109 might indeed boast superior maneuverability and a more favorable power-to-weight ratio, but if it faced a 30% chance of being destroyed by damage that a P-47 would readily survive, then the American aircraft was, in the final analysis, more effective. Pilot training consumed months and incurred costs far exceeding that of any aircraft. Experienced pilots became exponentially more valuable over time as they accumulated invaluable combat knowledge. The Americans clearly understood this critical calculus. The Germans understood it too, but their industrial capacities simply could not support the American solution. One particularly insightful section of the report addressed a factor that would have been almost heretical to mention within official Luftwaffe channels: pilot psychology and morale. The engineers observed that American pilots, fortified by the knowledge that their aircraft could absorb tremendous punishment and still ensure their safe return, would likely press attacks with greater aggression and disengage less readily. Conversely, German pilots, flying in more fragile fighters, would inevitably develop a sense of caution, would break off engagements earlier, and would be more inclined to avoid unfavorable encounters. This profound psychological factor effectively multiplied the P-47's material advantages. The aircraft was not merely mechanically superior in terms of survivability. It actively fostered a mental advantage that rendered American pilots more formidable opponents. The structural integrity of the P-47 Thunderbolt also garnered considerable critical evaluation. This formidable American fighter was meticulously constructed to rigorous assembly line specifications, a level of industrial precision that German manufacturing facilities were simply unable to replicate by 1943. Its riveting displayed remarkable uniformity and exactitude, while welding processes consistently yielded high-quality results. Furthermore, the aircraft's components were designed for complete interchangeability, a luxurious advantage that German maintenance personnel, accustomed to the laborious practice of hand-fitting parts and improvising repairs under duress, found almost beyond belief. This exceptional manufacturing prowess meant that even aircraft sustaining significant battle damage could be swiftly returned to operational status using standardized replacement parts. In stark contrast, German fighter aircraft frequently necessitated bespoke fabrication for repairs, a process that consumed invaluable time and highly skilled labor, both of which were becoming increasingly scarce resources. The comprehensive Rechlin report culminated in a series of recommendations that were, paradoxically, both eminently sensible and utterly unattainable. It posited that the Luftwaffe ought to implement redundant flight control systems, significantly enhance its self-sealing fuel tank technology, augment armor protection, and fundamentally re-engineer its fighter aircraft with survivability as a paramount design objective, rather than a mere secondary consideration. However, the practical realization of these proposals would have demanded a monumental effort, extensive retooling of factories, complete redesigns of existing aircraft from their foundational blueprints, and a substantial diversion of critical resources away from immediate production needs. Germany, by this stage of the conflict, simply lacked the requisite time, raw materials, or industrial capacity to emulate America's advanced manufacturing paradigm. Their only viable course of action was to meticulously document these crucial insights and harbor the slim hope that incremental, minor enhancements might, perhaps, marginally reduce the growing technological chasm. We invite you to stay with us and watch the end of this insightful video. We would be immensely grateful for your like and subscription. Please also consider sharing where you are from and your thoughts on the compelling topic discussed in the video by leaving a comment below. The detailed report was subsequently stamped with its classification, meticulously categorized, and then disseminated to the appropriate technical offices within the Luftwaffe's hierarchy. There, it joined a multitude of other intelligence documents, each serving as an uncomfortable testament to the undeniable truth that Germany was progressively losing the technological and industrial dimensions of the war. The profound implications of the Rechlin findings reverberated through Luftwaffe tactical planning like an undeniable seismic wave through still waters. Fighter commanders operating on the Western Front had harbored suspicions for many months that their established engagement doctrines were proving increasingly ineffectual against the robust American heavy fighters. Yet, mere suspicion and irrefutable, scientifically documented proof were distinctly different matters. Now, they possess concrete engineering data unequivocally confirming the observations and concerns that their pilots had been relaying. Engaging P-47s using conventional methods was demonstrably an egregious waste of precious ammunition and, far more critically, an unacceptable expenditure of invaluable pilots' lives. The Luftwaffe, facing this stark reality, found itself in urgent need of novel tactical approaches, and this necessity was immediate. The initial tactical adjustment, perhaps the most psychologically demanding for its pilots, mandated that German aircrews should, whenever feasible, avoid prolonged aerial combat with the P-47's. This directive directly contravened every deeply ingrained instinct instilled in fighter pilots, whose air combat doctrine rigorously emphasized aggression, relentless pursuit of attacks, and the decisive destruction of the enemy. Nevertheless, the Rechlin data conclusively demonstrated that a pilot flying a Bf-109 or Fw-190 could expend their entire ammunition load into a Thunderbolt without achieving a definitive kill. Conversely, that same P-47, even if damaged, possessed the formidable capability to effortlessly obliterate the German fighter with a single, precisely aimed burst from its potent .50 caliber machine guns. The mathematical conclusion was brutally unequivocal. Engaging in a direct exchange of fire with P-47s was an inherently losing proposition. Consequently, German tactical manuals began to emphasize highly specialized attack methodologies, meticulously engineered to maximize the probability of inflicting catastrophic damage. Pilots received explicit instructions to target the cockpit exclusively, if at all possible, this being the singular area where a single, well-placed hit could guarantee a kill, irrespective of the aircraft's inherent durability. However, this particular directive was considerably easier to conceptualize than to effectively execute in the chaos of aerial combat. The cockpit presented an exceedingly small target on an aircraft moving at high velocity, and American pilots were rigorously trained to constantly duck and weave, rendering precise aiming almost insurmountable. Despite the difficulty, this approach was deemed superior to the futility of expending ammunition on the P-47's resilient wings and fuselage, which were designed to absorb such impacts. Another critical recommended tactic involved initiating attacks from a direct frontal aspect, utilizing head-on passes. This head-on approach achieved two crucial objectives simultaneously. Firstly, it afforded the German pilot a fleeting opportunity to strike both the cockpit and the engine, thereby maximizing the potential for critical damage. Secondly, and equally important, it effectively neutralized the P-47's inherent advantage in defensive armament. The Thunderbolt's formidable array of guns was exclusively mounted in its wings, meaning their cone of fire converged optimally at a specific range, typically around 300 yards. At distances either closer or farther than this optimal range, the concentration of fire diminished significantly. A head-on pass transpired with such blinding speed that both pilots had only a mere fraction of a second to discharge their weapons, and in that fleeting moment of geometric alignment, the German aircraft's centrally mounted cannons possessed a slight, yet potentially decisive, advantage. Naturally, engaging in head-on attacks was an utterly terrifying experience, profoundly psychologically demanding, and necessitated an almost superhuman level of courage. Closing on an adversary at a combined speed exceeding 600 miles per hour, with both pilots hurtling directly towards each other, neither willing to be the first to break formation, transformed each encounter into as much a brutal test of raw courage as it was a demonstration of piloting skill. A segment of Luftwaffe commanders advocated for a more pragmatic approach, simply disregarding the P-47 escorts entirely, and instead focusing their efforts exclusively on the heavy bombers they were protecting. This, after all, constituted the Luftwaffe's fundamental mission, the systematic destruction of the American heavy bombers, which were relentlessly and systematically dismantling Germany's industrial infrastructure. If the P-47s proved too resilient and difficult to dispatch efficiently, then perhaps a more effective tactic involved accepting their presence, utilizing superior numerical strength to lure them away from the vulnerable bomber formations, and then striking the B-17s and B-24s while their escorts were momentarily out of position. This particular strategy did yield occasional successes, but American fighter tactics swiftly evolved to counter it. P-47 units began to implement layered escort formations, wherein a contingent of fighters maintained close, protective proximity to the bombers, while other elements conducted independent, free hunting patrols at various altitudes, poised and ready to intercept any German fighters that dared to appear. The profound psychological ramifications of the P-47's astonishing durability extended far beyond mere tactical adjustments. German pilot morale suffered a significant blow when they grasped the demoralizing realization that they could execute every maneuver flawlessly, achieving a perfect attack vector, landing multiple direct hits, observing their ammunition strike home with undeniable impact, and yet still watch the American fighter disengage, perhaps trailing a plume of smoke, but fundamentally operational and capable of continuing its mission. This created an overwhelming sense of futility, fostering a pervasive feeling that the enemy possessed technological advantages so profound that even the utmost skill and bravery of individual pilots could not hope to overcome them. This particular aspect proved especially disheartening for the seasoned, experienced pilots who had meticulously built their reputations over years, predicated upon their exceptional marksmanship and tactical prowess. They had dedicated countless hours to mastering their craft, and now, that hard-won mastery seemed woefully insufficient when pitted against the formidable capabilities of American engineering. Maintenance and logistics officers, analyzing the Rechlin report from their unique perspective, drew their own critical conclusions. If P-47s were consistently returning to their bases with damage levels that would have irrevocably destroyed German fighter aircraft, it logically implied that American maintenance crews were expending an enormous amount of effort repairing damaged aircraft rather than focusing solely on the production of new ones. This observation hinted at a potential vulnerability within the American logistics chain. The strategic implication was clear. If the Luftwaffe could inflict more damage on P-47s than American maintenance facilities possessed the capacity to repair, they could effectively diminish the enemy's operational numbers without necessarily achieving definitive aerial kills. This crucial insight ultimately led to a subtle yet significant reorientation in mission planning. On occasion, the very definition of mission success was subtly redefined from destroyed in the air to damaged enough to be out of action for several days. By the early months of 1944, Luftwaffe commanders had come to a profound understanding. They were engaged in a conflict against an adversary whose fundamental industrial philosophy diverged dramatically from their own, and this inherent difference was manifesting itself in a combat effectiveness that could not be adequately countered by tactical adjustments alone. The P-47 Thunderbolt's remarkable performance under direct fire during the Rechlin evaluations transcended being merely an intriguing footnote in Luftwaffe intelligence reports. It represented a pivotal moment, fundamentally reshaping how military aviation would henceforth approach the core question of aircraft design priorities. The ensuing post-war decades would conclusively demonstrate that the indelible lessons gleaned from that bullet-riddled aircraft profoundly influenced the trajectory of fighter development on both sides of what would soon become the global Cold War divide. The guiding philosophy of constructing aircraft designed for inherent survivability, rather than solely emphasizing maneuverability, rapidly transitioned from a topic of debate into established doctrine. American aircraft designers meticulously absorbed the P-47's exemplary combat record and proceeded to refine this concept even further. The Republic F-84 Thunderjet, a formidable aircraft developed in the late 1940s, directly inherited the Thunderbolt's robust design DNA. It was heavy, exceptionally fast, and engineered from its inception to absorb significant punishment in combat. This enduring design philosophy extended its influence far beyond the realm of dedicated fighter aircraft, permeating the development of specialized attack aircraft, such as the A-10 Thunderbolt II. Introduced into service in the 1970s, and remarkably still operational today, the A-10 essentially represents the P-47 concept taken to its ultimate, logical extreme. It features redundant flight control systems, a heavily armored cockpit, advanced self-sealing fuel tanks, engines strategically positioned to offer mutual shielding from ground fire, and the extraordinary capability to return to base even after sustaining damage that has effectively shot away half of its airframe. The very existence of such an aircraft is a direct testament to the P-47's foundational proof that the concept of survivable design unequivocally worked. Soviet aircraft designers, for their part, diligently studied captured German intelligence reports concerning Allied aircraft, including the highly illuminating Rechlin findings. Consequently, post-war Soviet fighter designs exhibited a growing and pronounced emphasis on enhanced pilot protection and comprehensive system redundancy. This philosophy became overtly apparent in aircraft such as the Su-25, which served as the Soviet Union's direct equivalent to the A-10, incorporating many of the identical or highly similar survivability features. The myriad proxy conflicts that characterized the Cold War era, ranging from Korea and Vietnam to Afghanistan, provided endless and undeniable validation that aircraft specifically engineered to ensure the safe return of their pilots were unequivocally worth any associated weight penalties. Even the Germans, despite their initial resistance, ultimately assimilated these crucial lessons, though their understanding arrived too late to significantly alter the outcome of the conflict. Late war designs, such as the Ta-152, demonstrably showed increased attention to pilot protection and the resilience of fuel systems. Furthermore, the nascent jet aircraft programs, particularly the groundbreaking Me-262, began to incorporate self-sealing fuel tanks and improved armor as standard, integral equipment, rather than treating them as mere afterthoughts or supplementary additions. While certain design considerations, such as robust structural elements and protective systems, were belatedly integrated into German aircraft development, they often remained secondary considerations rather than foundational principles. Consequently, by the period these crucial refinements began to materialize on frontline combat planes, the German war machine was severely constrained, lacking essential aviation fuel, a sufficient cadre of highly skilled aviators, and the requisite industrial capacity to implement any meaningful strategic impact. The once formidable Luftwaffe, which had earlier spearheaded revolutionary modern air combat tactics and aerial doctrines, ultimately found itself utterly engulfed and outmaneuvered by adversaries who had not only perfected advanced tactical maneuvers, but also achieved unparalleled supremacy in industrial production capabilities. The tragic toll on human lives, directly attributable to these differing engineering philosophies and design choices, became strikingly evident when a comprehensive analysis of pilot loss rates was conducted. American fighter pilot casualty figures in the European theater, though certainly not negligible and representing significant personal tragedies, were nevertheless markedly reduced when juxtaposed against their German counterparts, especially during the climactic and brutal final years of the conflict. A portion of this pronounced divergence in casualty statistics could be attributed to the Allies' overwhelming quantitative advantage and superior pilot training regimens. However, a major factor undeniably stemmed from the inherent resilience and structural integrity of their aircraft. American aviators frequently emerged unscathed from catastrophic crashes and sustained combat damage that would have irrevocably claimed the lives of their German adversaries. For instance, the robust P-47 Thunderbolt possessed the remarkable ability to endure extensive battle damage, often being riddled with ordnance, yet still managed to successfully traverse the perilous expanse of the English Channel and return to base. In stark contrast, a Messerschmitt Bf 109 sustaining comparable damage would invariably compel its pilot to jettison from the crippled aircraft, often over hostile territory, leading to an almost certain capture at best. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. The enduring influence of this engineering philosophy, prioritizing pilot and aircraft survival, extends far beyond its initial military applications. Indeed, the unwavering commitment to redundancy in modern commercial aviation, characterized by the integration of multiple backup systems for virtually every critical operational function, finds its foundational principles in the very same engineering mindset that gave birth to the P-47. Illustrative examples abound. The iconic Boeing 747's quartet of powerful engines, the sophisticated triple-redundant hydraulic systems ubiquitous in contemporary airliners, and the meticulously designed elaborate fire suppression mechanisms all eloquently underscore the profound lesson that ensuring the safe return of human occupants unequivocally validates the acceptance of additional structural weight, increased system complexity, and heightened manufacturing costs. The specific P-47 Thunderbolt subjected to rigorous evaluation at the Rechlin testing facility almost certainly did not endure the entirety of the conflict. Historical accounts indicate that the majority of captured enemy aircraft present at the installation were either annihilated during intense Allied bombing raids or systematically dismantled by retreating German forces, a preemptive measure to preclude their recapture and potential exploitation. Nevertheless, the aircraft's profound influence persisted vibrantly within the intellectual sphere of every engineer and pilot who meticulously scrutinized those comprehensive test results. They had observed undeniable evidence that an aerial platform could be conceived and constructed to withstand a degree of punishment previously considered utterly unsurvivable. This compelling proof fundamentally altered perspectives on the architectural principles governing the construction of future combat aircraft. In the contemporary era, the survivability of military aircraft stands as a paramount design imperative, integrated from the initial ideation phases and conceptual sketching, never relegated to a secondary concern or mere afterthought. While technological advancements such as sophisticated stealth capabilities, intricate electronic countermeasure systems, and revolutionary advanced materials have undeniably transformed the specific tactical approaches employed, the core tenet of this design philosophy endures immutable. The most exemplary aircraft is ultimately defined by its unwavering ability to safely deliver its aviator back to base. The P-47 Thunderbolt, stoically positioned within that German test range, valiantly withstanding barrages of 20mm autocannon rounds and demonstrating incredible tenacity by refusing to yield, unequivocally validated that fundamental concept in the most direct and undeniable manner conceivable. The German engineers had initially endeavored to decipher the perplexing phenomenon of why these American fighter aircraft consistently endured such severe punishment. They received their definitive answer, meticulously recorded their findings with exhaustive detail, and in doing so, contributed significantly to charting the course and establishing the foundational blueprint for every subsequent combat aircraft design. The rigorous evaluation conducted by the German specialists was initially intended to uncover inherent weaknesses and structural deficiencies within the captured airframe. Contrarily, it unveiled nothing short of a paradigm shift in aviation design philosophy, a profound conceptual breakthrough that would not only transcend the immediate confines of the Second World War, but also endure beyond the protracted period of the Cold War, persistently shaping and informing aircraft design principles well into the 21st century.